Hello everyone, this is David Matkin, and in this video I want to talk about the relationship between a nominal rate of return, often referred to as the APR, and the effective rate of return, which we often call the EAR, sometimes the APY, or the annual percentage yield. And we're going to do some calculations to try and wrap our arms around this idea. And I've got some things up on the screen that you should be used to or be familiar with from some of the other information we've dealt with, where we'll look at a situation where we have an APR, an annual percentage rate or a nominal rate of 6%, and we will consider having a present value of $100, and we'll look at this investment over 2 years. Or it doesn't need to be an investment, it could be the cost of something in the present is $100, and how much will it cost us 1 year into the future given an APR of 6%. So what I have down here in this table is information. We'll look at this with the same 6%, $100, and over 1 year. We will look at a compounding frequency of 1 year, or of 4 quarters, which is the same as 1 year. Also 12 months, or 52 weeks, or 365 days. All right, so this is the compounding frequency per year, and therefore the total number of compounding periods that the interest rate gets applied. And the interest rate we're using is the APR here. That's what we're feeding into the future value formula. And the rate that we're going to use is going to be this 6%, but we'll divide it by the number of times we compound per year. And so we've got 6% divided by 4 for quarterly, or 6% divided by 12 for monthly. And when we do our future value calculation, therefore, what we're going to provide the Excel function is information on the amount we start with, and then the number of periods that are different between, or separate, the starting value and the ending value, and the amount of growth that occurs on each dollar between the starting value and the ending value. All right, or each period until we get to the ending value. So when we compound annually, we take this present value of $100 and apply the 6%, but we wait all the way to the end of the year, so we only have the one compounding event. We only have the one moment that we recognize the change in the value of the dollar, or the time value of money is applied. And so let's just calculate this. The future value will feed in this rate information, we'll feed in the 1 period, and there's no annuity that's going to occur every compounding period. There's just a present value that rises to a future value. So we'll feed in the present value. I'm going to put present value as negative. I'm wanting the ending result to come out as positive. So I stop and say, well, how do I get this to come out as positive, the present value input? I put a negative in front of it, and it treats it like it's an outflow in order to result in an inflow. All right. So I get this $106, and that's not surprising, right? That is a 6% of $100 added on to the $100 in total. So effectively, this $100 grew by 6%. In fact, if we calculate the effective interest rate, or the effective annual rate, and we put this 6%, and I'll lock that in, and we look at it over one compounding period per year, we will see, yeah, the effective rate is 6%. So this future value, even though it rose to $106, it's not really defined by this 6%. We could say that's the effective growth of the dollar is 6%. So it's not defined by the APR 6%. The APR gets transformed by dividing it by 1 and then applying one event of compounding to it, and therefore it stays at 6% of having a 6% effect. So that might not make quite as much sense when we are dealing with annual, but let's drop down to quarterly. So when we have quarterly compounding of the same $100, we'll actually end up, I didn't reference in my $100. Gotta lock that in. So actually see that that investment grows to something greater than $106. So this is really critical for us to recognize that the function, the future value function, and all those time value money functions always produce a calculation or produce results that reflect the effective annual return on the dollar, right? Because we divide the rate by the number of times we compound per year, and we multiply the number of periods by the number of times we compound a year. That little transformation makes it so this 6% gets changed and actually has a larger effective rate of growth than 6%. All right, so this means that if we look at the effective rate of growth, the true effective rate of growth when we do quarterly compounding, so I'm feeding in the 6% as the nominal, and then the 4 as the number of periods per year, we see that the effective rate of growth is 6.1364. Well, that's exactly what we see the $100 growing by. So that is the effective growth on the dollar, and we fed in this APR information, and we manipulated the APR information to be a quarterly rate, and number of periods was now quarterly, and the result is that every dollar actually grew. So these future values are all results of the true effect on the dollar. We feed it in the APR, but it's actually grows by the effective rate of growth. And the effective rate of growth is due to the increase in the compounding frequency. So let's see, as we compound more frequently, the effective rate of growth is larger, like it has a bigger effect. So we can see this if we look at the EAR. And this just means that $100 is going to grow to something a little larger every time we compound more frequently. Now, the difference between 52 or weekly compounding and daily compounding is not really substantively significant here, at least not over 1 year. But the more we compound, still, the more frequently we compound, still the more the dollar will actually grow, and the future value calculation will represent the true effective growth of that dollar. Right? This is a really important concept. So that the APR becomes kind of a shorthand for talking about this rate of growth, but it's not the true effect of the rate of growth. I think one example that makes sense to me to think about this is when we look at our weather app and we see that what the temperature is, it's not really what we feel as a temperature. It's just the baseline information. To understand what it actually feels like, we need to incorporate things like, is it sunny or cloudy? Is it humid or dry? Is it windy, or is the wind a cold wind, or is it a hot wind? You know, there's a bunch of other conditions that could affect what the temperature actually feels like or what the true effect of the temperature is. But we still start usually with the nominal temperature when we talk about temperature. And then we make adjustments based on what the prevailing conditions are. That's not exactly the same comparison, but it shows us that we often use a shorthand number that then has to be adjusted in order to get to its true effect. And in this case, the adjustment is done by dividing by the number of the rate by the number of compounding periods, or the nominal rate by the number of compounding periods per year, and then also multiplying the number of years by the number of compounding periods per year to get the total number of periods. And by starting with the APR, we can deal with periods that are different than just annual periods. We can deal with 2.5 years or 2.25 years or something like that. And it doesn't limit us to just being able to deal with annual rates or annual periods. So I hope that gives you some insight. I'm going to keep going and hopefully add a little bit. But if you need to stop and watch that again, please do. Let's look here at this idea of these formulas. So here's this $100 that is being adjusted, right? That's the present value of $100. And here's the 6% rate. Here's the 6% rate divided by 4. Here it is divided by 12. Here it is divided by 52. Here it is divided by 365. And here's the change in the number of periods that rate is applied. And this adjustment over here on the right is what creates a difference between the nominal rate, which was what we start with, and the actual effect. And so this will give us the same calculations that we see over here with using the future value formula. It's the same, the effective, the true effect of an interest rate growth will be the same whether we use the time value of money functions in Excel or whether we use financial calculator or whether we use algebra. All right, because we're doing this division of the rate and multiplying the number of periods, the number of years by the compounding periods per year, we are effectively changing how much the every dollar grows by. So as we increase the compounding frequency, the true effective rate of return will be larger and larger than the nominal rate. So if we take that information and then we say, well, what happens if we start with an effective rate of return? What does that do? How do we take a fixed effective rate of return and then see how that would change how we would deal with these calculations? So we, instead of starting with the APR, well, it's just the inverse situation where when we went from APR to the EAR, as we got to a higher frequency of compounding, the EAR got larger. In this case, if we hold the EAR constant, that would be holding this information right here constant, but allowing this percentage to change in the nominal rate that we feed into Excel or feed into the formulas, then the rate is just going to decline. The APR is going to get smaller. The APR that is equivalent to this 7% will get smaller as we compound more frequently. So I can say, what is the nominal rate for this 7%? I'll feed in the effective rate, lock that in, given that we're compounding annually. Well, we already know this from above. the effective rate and the APR are the same thing if we're only compounding annually, because the effective every year, if the effective every year is 7%, then the APR that's equivalent to that is 7%, because it's the compounding happens every year. But if we move that over to quarterly, we're going to see the APR that is equivalent to this EAR or this effective rate of 7% being something smaller than 7%. Okay, so look, we do the effect function, or the effective rate of 6.823, and look at the number of periods per year, 7%. All right. So that's just reversing that calculation, okay? So here, this 6.823, if we feed this 6.823 into a time value of money function, but treat this annual percentage rate as quarterly compounding, it will grow annually at the same amount that if we use the 7%, but only compounding annually. So so that means that this future value at this effective this APR for annual will produce the same or be equivalent to the same present value as this 6.823 quarterly APR. So let's just work this out, all right? So we're going to do it over 35 years. I'll lock that 35 years in and multiply it by the number of periods. And so there are more quarters. So let me insert here, I'll put rate so that we can see this. We don't have the rate for any of these, but we'll take the 7% and divide it by 1, right? And we'll take this 6.823 and divide it by 4. So now we can calculate the present value of this same amount. Recognize that we're going to feed different APRs into the formula, but both of these APRs are designed to be equivalent, to have the equivalent effective rate of return. And remember, the true effective rate of return is what explains the true difference between the future value and the present value. So we'll use the present value function. We'll feed in the rate. The number of periods is the total number of periods that we're experiencing this over. And we don't have an annuity, and we're going to just feed in this future value. I'll put it in as a negative, and so it will come out as a positive. So that gives me a present value of $9,366.29. If I invest $9,366.29 today, and it grows at an effective rate of 7%, then we'll raise up to $100,000. Now, I want you to think about what this answer is going to be. What's going to happen? What's the present value going to be of the quarterly rate? Pause, think about it, do the calculation on your own, or whatever you need to do to sort of work your way through this. Remember, we lowered the APR, but that's still what we're feeding into this present value formula. So I could autofill it over, but I think it's helpful for us to walk this through. We're going to put in this lower APR, right? We're putting in a lower APR than the 7%, but we're going to allow it to have a lot more compounding periods. There's still no annuity, and we'll feed in this future value of the 100,000. I'm going to lock it in so that I can autofill after. Boom, the exact same amount. Because what really explains the difference between the future and the present is how much the dollar actually changes, or how much each dollar actually changes. And that's the same way of saying the effective rate. And so this APR was calculated in order to produce the equivalent effective rate of 7%. So every one of these APRs is going to be a little bit lower because we need to have a little bit lower APR in order to produce the same effective rate. So all of the rate inputs are going to be smaller, but the total number of compounding periods is going to be larger, and therefore we produce the exact same present value, or it's the equivalent present value. And this should be the same across these different ways of doing the calculation, because we forced all of these calculations to have the exact same effective rate of 6% or of 7%. Up here, we had the same APR, but they have a different effective rate. Here we said, let's lock in the effective rate at 7%, and let's adjust the APR so that when we then run that APR through the time value of money function, it will have the proper 7% effect. And the time value money function is always, those results are always going to reflect the effective change. We're feeding in the nominal information, but because we are doing the division and the multiplication based on the compounding frequency, the true effect will be integrated into the end calculation. All right, so I know this is a lot, but it hopefully it helps you wrap your brain around conceptually what's going on. If I know that I have some amount of money in the future, and I know the effective rate of return is 7%, I can just do this annual calculation for how many years it is between that time in the future to present. And I can just feed in the 7% because the 7% effective rate is the same as 7% annual. If I want to use a monthly transformation on that money, I have to to do that, I have to adjust the effective rate to find out what its equivalent nominal rate would be, and I have to adjust the number of periods that I'm looking at, but it's going to give me the exact same result. So this would be the same thing as having a present value of a future annuity and trying to figure out what the PV0 of that deferred annuity is and walking it back. If you know the effective rate, then you can walk it back or discount it back or calculate its present value, PV0, using just the annual representation. But if you want to use quarterly or monthly, you can. You just have to do some extra steps. Okay, that's enough. I hope it's helpful. Might be something to pause, think about, work through.